Welcome to Homework Lib.
Over here we have the following setup, which a charge q, unknown, is at the very middle of one of the sides of length a of a square, which has the same charge q on all of the sides. So essentially, what we want to draw here is the diagram of the forces and calculate the value of the forces acting on this one. So first of all, the forces acting from charges 1 and 2, I'm going to put it in green over here. They're going to cancel out each other. So these forces, they are not going to be necessary for our drawing. On the other hand, what is going to happen is that we're going to have the forces coming from charges 3 and 4 that here I'm assuming that all of the charges have the same sign, just for sake of the drawing, that are going to be looking like this. What this means, because both of them are going to have the same magnitude, because they are going to have the same distances, what is going to happen is that the sum of the forces on x are going to be equal to 0, because if we take the projection of each of these forces on the x-axis, they're going to cancel out each other. And the sum of the forces on the y-axis is going to be equal to 2 times the magnitude of the force of y acting from q to q3 or q4, because they are going to have the same size and we have two of them. So with this, we have already kind of solved the problem without having to do any calculation, just by looking at the force diagrams. So now let's proceed with the actual calculation. So as we said, the sum of the forces on x is going to be equal to 0 directly. Now the information that we require is going to be the forces on y. So the very first step is going to be to find this distance over here. To find the distance, we know that we have a right triangle, which is going to have a side of a, the other side is going to be a over 2. So the distance d is going to be equal to the square root of a squared plus a squared over 4, because this is a over 2 squared. So this is going to be equal to a square root of 1 plus 1/4, which is a times the square root of 5 over 4, which is a over 2 square root of 5. So we're going to have directly the distance over here. So now the sum of the forces on y is going to be equal to the force of q coming from q3 on the y-axis plus the force of q from q4 on the y-axis. In this case, both of them are going to be the same, so we can directly calculate it as 2 times the force of q3 acting on y. I'm going to use q3 as reference in this scenario. So now that we know the distance, we can know, for example, the angles. So in this case, to have the correct angle, I'm going to use this guy as reference, this angle theta, which is going to be the same as this angle theta over here. So to find that, essentially what we have is that the tangent of theta will be equal to a, the opposite catet, divided by adjacent catet, which is a over 2, which is 2. So theta is equal to arctangent of 2, which is equal to 63.435 degrees. So that value of theta is going to appear on different parts over here. Let me clean up a little bit the drawing over here, just to make it more clear where we are standing. So in this case, theta would be the angle over here, theta, and also the angle over here, theta. So the y projection of the force corresponds to the opposite catet on this right triangle. Whoops. Let me go a little bit up just to make the drawing. So this is going to be the y component of the force of q3 acting on Q. And as you can see, this is equal to 2 times the absolute value of the force of Q from Q3 times the sine of theta. So this would be 2 times K, whoops, over here, 2 times K Q times Q divided by distance squared. And this distance squared would be a squared 5 times a squared over 4, which gives us 8kqq over 5a squared. And all of this multiplied by sine of theta. So this would be the sum of the forces on y directly 8 times kqq over 5a squared sine of theta, where the angle theta is this value over here. Now the question states what would be the charge that makes this go into equilibrium if it is put right in the center over here. Let's call this charge QE for charge of equilibrium. First of all, the center is at a distance of a over 2. So for the sum of the forces on y to be equal to 0, we would have a times kqq over 5a squared sine of theta plus the force of this equilibrium value. So this would be hqq sine of theta over 5 times a squared plus k, this equilibrium charge, times q, divided by a over 2 squared. So a squared, and over here a 4. For this to be equal to 0, we would have that QE would be equal to minus 8kqq sine of theta over 5 times a squared multiplied by the factor of a squared over 4kq. Let's cancel everything that can cancel out. A squared and a squared cancel out. 4 and 8 cancel out to get to 2. Kq cancels out with kq. And we're going to get that the charge E that puts our system in equilibrium would be equal to minus 2 times q sine of theta over 5. And with that, we're done with the problem. So just to summarize, the first thing that we did was, here I'm considering that all of the charges have the same sign because there's no minus in front of the values of q minus and q as block matches or as caps lock. So the force diagram looks like this. We can evaluate what is the sum of the forces of y coming from that, and we find the angle from the geometry of the problem because we know that we have a squared. We know that we have a and a over 2 as sides over here for this right triangle, and with that we find the corresponding angles. So now with the angles, what we say is that if we put a charge right at the center of the square, what would be the value for the charge QE for it to be at equilibrium? And essentially what we did was adding up that additional force, noticing that that force only contributes to the y-axis for this scenario, and solving for the value for QE, which gives us this final result. So with that, it would be all. Thank you very much and have a good one. Happy face.